Hey guys, so I wanted to break down two of these shorter free response with you. All right, so I'm looking at the back page of one of the free responses that you have, or the ones that have these ones. They're both from 2017. All right, and they only have one or two questions on them. All right, so let's work our way on this top one. It's number 3. It says at high temperatures, N2 and O2 can react to produce nitrogen monoxide, right, as represented by the equation above. Right, it says write the expression for the equilibrium constant Kp for the forward reaction. All right, so seemingly easy enough, and it is. You just got to be careful. If it's a Kp expression, it's a little bit different. You don't use brackets. You have to use parentheses, and you don't write the substance in the brackets. You put a P for partial pressure with what it is after it. Right? So again, no pure liquids or solids, right? But it's going to be products to the power of their coefficient over the reactants to the power of their coefficient. So parentheses P NO squared over parentheses P N2 to the first, parentheses P O2 to the first. So there's a good Kp expression for you on that one. For B, it tells us that a student injects N2 and O2 into a rigid vessel and then raises the temp to 2000. At this temp, the initial partial pressures of the N2 and the O2 are 6.01 atmospheres and 6.61 atmospheres respectively. The system gets to equilibrium, and the partial pressure of NO at equilibrium is 0.122. Calculate the Kp. All right, so if they're wanting you to get equilibrium concentrations or pressures, or they're asking you to get the K, the most common way to do that is to look at an ice table. Right, so we start with our equation, the N2 plus the O2 going to the 2NO. Set up our ice table. They gave us our initial partial pressures of each. Right, the N2, 6.01 atmospheres, the O2, 1.61. Right, be careful, all right? It says the partial pressure of NO is 0.122, but that's at equilibrium. This is our initial line, which means we don't have any of it to start. Equilibrium is going to shift toward the side with the 0 to get to equilibrium. Again, because if you do a QK comparison, right, when you do your products over reactants, you're going to have 0, right, and there's nothing less than 0. So Q is less than K. It will be a shift right. Right, that means this is minus X, plus, and be careful here, 2X. Drop these guys down, 6.01 minus X, 1.61 minus X, and a 2X. Next thing we usually do is plug into our Kp expression. Kp expression says take the pressure of the NO and square it. So we're looking at 2X squared over each of these guys. 6.01 minus X times the 1.61 minus X. Okay, now they want us to get the Kp, and when we get to this point, it seems like I don't have enough information, right? Don't have K, don't have X, and when that happens, I always say there is other information out there that will let you solve for X. And that other information is the 0.122 atmospheres. So they're telling us the NO at equilibrium, this guy, equals 0.122 atmospheres. So now I can solve that equation for my X. So if I do that, my X is going to be the 0.122 cut in half. Looks like 0.061. And then we can plug that value into this equation. All right, so we'd be looking at 4x squared over, right, the 6.01. And then I'll plug this guy in. 4 times the 0.061 squared over 6.01 minus 0.061, and then 1.61 minus 0.061. All right, and then we get our number. So 0.061 squared, right, times that by 4. Right, divide by the 6.01 minus 0.061 in parentheses there. And then divided by 1.61 minus 0.061 again. And if you do that upright, you're getting a value of 1.6 times 10 to the negative 1, 2. So you're getting a negative 1.6 times 10 to the negative 3rd. All right, so pretty standard presentation of that. All right, then the second one on that page, all right, says answer the following questions about the MgOH2. This was question number 6. It says at 25 degrees, the value of the solubility product constant, KSP, for the MgOH2 is 1.8 to the negative 11. It says calculate the number of grams of MgOH2 that's dissolved in a 100 milliliter container of saturated MgOH2. All right, so I want to get grams of this, right? And I know a volume, all right? And the only other stuff they have listed up above is this KSP. And you have to understand, like, KSP has a very specific equation linked with it. It's always a solid going to the ions. So there is a hidden equation in this. You've got the MgOH2, which is a solid, going to the Mg plus 2 plus 2OH negative. All right, so now that we have an equilibrium that we're working with, right, and they give us a K, we can find out something that will help us toward getting the grams of MgOH2. All right, so just like all these, if I see a K expression, there's a really good chance I'm going to do an ice table. Right? In these KSP ones, remember, the solid's always dashed out because we don't list pure solids. Right? We don't have any of the ions initially, which means we'll be shifting to the right. So we're looking at plus X, plus 2X, and then X and 2X here. Then we plug into our K expression. Right? So our KSP would have been the concentration of Mg plus 2 times the concentration of OH negative squared, because the coefficient of 2, all over 1, because we wouldn't list the pure solid. Then we plug our terms in. So we're looking at X and then 2X squared, all over 1. So you simplify the math there. Looks like we have 4X cubed, and we know what the K is. It's 1.8 times 10 to the negative 11. And the reason this can be useful is it can let me find the molarity of one of these substances. And if I have a molarity in a volume, right, because I know the 100 milliliters, I know I can always get to moles, and moles can take me a lot of places. All right, so we're going to solve this guy for X. All right, if I do that, looks like I'm going to take the 4 and divide to the other side, 1.8 times 10 to the negative 11, divide that by 4. And then you're third rooting that, or you could raise it to the 1/3 power. All right, so when I put this in my calc, I hit 1.8 e negative 11, and then I divide that by 4. Then I hit caret, parentheses, 1 divided by 3, enter, right, and I get an X value of 1.7 times 10 to the negative 4. Now, you have to understand who that is. All right, X represents the Mg plus 2. And that's fine. We just need to know who we're working with. All right, so now I have a molarity, and like I said, I had a volume, so what I can do, right, is use it. I have 100 milliliters, 0.100 liters. I have a molarity, 1.7 moles, Mg plus 2 per liter. That's times 10 to the negative 4. Now I can convert my Mg plus 2 into the MgOH2, right? Looking at that formula, that's a 1-to-1. And then last but not least, I can take my 1 mole MgOH2 into grams, and they were nice enough to give us the value. It's 58.32. All right, so to finish things up on this guy, 0.100 times the 1.7 e negative 4 times the 58.32. And I get 9.9 times 10 to the negative 4th grams. Hope that helps you out. Shoot me a message if you have any questions.